Okay, in this video I'm going to work through some, just proving some different infinite series, and just as you watch this, pay close attention to the write-ups. So first thing I do on this one is I notice that this is the same thing as 1/2 to the n, which is clearly a geometric sequence, so you'd say geometric series with r equal to 1/2, which is less than 1. Therefore converges. Okay. Next one, this one is also it's not a geometric series, but it looks kind of like a p-series, but it's not, of course. So first of all, we want to look at that and say, let's see, how can we rewrite this to get a handle on it? N equals 2 to infinity. That would be 1 over n times n minus 1. This is to the 1/2, and that's to the 1/2. So my a sub n is going to be 1 over, I guess I'll leave it like that actually. And my b sub n is going to be, basically I want it to be 1 over, I want it to be a p-series, so it has to be a p-series, so, but I want the degree of the p-series to match roughly what this would be. So this n is raised to 1/2 power, and then multiplied by that n. So that essentially would be n to the 3/2 power, but it's also square rooted. So that would be n to the 3/4 power. So we're going to make that 3/4. Okay. So then, and we know that that is a divergent series, so then we want a sub n to be bigger than that, which is, or we can just do the limit. So I think I'll just do the limit comparison test. So the limit of a sub n over b sub n, that would be basically n to the 3/4 over square root of n times the square root of n minus 1 as n approaches infinity. And so that would be just 1. And since that's greater than 0, that means that the two of the series behaves the same. So we say since b sub n is a p-series with p greater than, less than 1, it converges, it diverges, and therefore a sub n also diverges. Okay. So let's see, look over here. This has a 3 to the n and a factorial, so that makes you think ratio test. So I'm going to do ratio test. So that would be the limit as n approaches infinity, 3 to the n plus 1 over 2n plus 2 factorial times 2n factorial over 3 to the n. And so then the 3n and 3n plus 1 and 3n cancel out, leaving a 3. And the 2n factorial and the 2n plus 2 factorial cancel out, leaving a 2n plus 2 on the bottom times 2n plus 1. And if we let n approach infinity, that equals 0, which of course is less than 1. So therefore, my original series diverges or converges because the ratio is less than 1. Converges. All right, this one is a if we can rewrite this as -1 to the n. Oops, got to leave my -1 to the n times 1/3 to the n. So if we wanted to use the alternating series test, we could show that we'll choose our a sub n to be 1/3 to the n. And that is always positive. A sub n is positive for all n. A sub n is decreasing because because 1/3 to the n plus 1 is less than 1/3 to the n. And the limit as 1/3 to the n as n approaches infinity definitely goes to 0. Right? So therefore, passes all the 3 requirements. Therefore, -1/3 to the n as n from 0 to infinity converges. All right, here's another looks like alternating series test. We can let choose a sub n to be n cubed over n squared. Oh, no, don't want to do that because that won't pass the test. It's not decreasing, and it definitely doesn't go to 0. Whoops. So we don't want to do that. Actually, we could just take the nth term test. Nth term test. Limit of -1 to the n cubed over n squared as n approaches infinity goes to, well, it does not equal 0. Therefore, this thing diverges. It's supposed to be -1 there. This is just a geometric sequence. Geometric series with r equal to 2, which is greater than 1, therefore it diverges. You could also use the nth term test to prove that diverges. Pretty straightforward. Okay. There's another alternating series test. You could just you could run through the similar one I just did. You could show that it is definitely positive for all n, and so you pick your a sub n to be 1 over the square root of n, and it's decreasing because n plus 1, square root of n plus 1 is bigger than square root of n, and that definitely goes to 0. So you could prove that it converges. So here's another different one. This one is the one I'd use the nth root test on, or the nth root test. So you take the limit as n approaches infinity of the nth root of the absolute value of -2 over n plus 1 to the n. So of course that's just equal to the limit as n approaches infinity the nth power nth root cancel out, absolute value takes care of the negative. So that would be 2 over n plus 1, and that approaches 2, which is, well, is greater than 1, then a sub n is divergent. Since this is greater than 1, that means that that original series is divergent. Okay. Here's a great example of, well, let's see, what could we do here? This is we could try a ratio test here. Ratio test. So that'd be the limit as n approaches infinity of the absolute value of n plus 1 times pi to the n plus 1 over -3 to the n times -3 to the n minus 1 over n times pi to the n. And that's going to be equal to the limit as n approaches infinity. Okay. So the pi to the n and the pi to the n plus 1 would cancel out, leaving just pi on top. And the n plus 1, of course, doesn't cancel out with anything, so it's just going to be a pi there. These guys cancel out, leaving just a -3 on the bottom. And there's an n on the bottom. Of course, the absolute value takes care of the -3, so we're going to have the limit as n approaches infinity of pi times n plus 1 over 3 n, and that ends up being pi divided by 3, which is slightly bigger than 1. Therefore, my original series diverges. Diverges. This one looks like a potential integral test, so I'm going to try that. Since we haven't done one of those for a while, f of x is equal to x squared e to the -x cubed. And so then we need to show that that's positive. So x squared over e to the x cubed. Since x squared is positive and e to the x cubed is positive, this is going to be greater than 0 for all x. And it is decreasing. We could show the derivative of f of x is going to be low d high, so that'd be 2x e to the x cubed minus high d low, which would be e to the x cubed times 3x squared. All that's over e to the x cubed squared. And if we simplify that, what do we got here? We got a 2x e to the x cubed minus 3x to the 4th e to the x That's supposed to be x cubed, isn't it? All over e to the 2x cubed. Okay, so the bottom is always positive, and the top, since this portion is bigger than that, we know that that's always going to be less than 0 for all n. And then finally we need to show that f of x is continuous for all x. Actually, it's continuous for all x because e to the x cubed is always never 0. Okay, so now we just got to take the integral. So we're going to take the integral. Well, first of all, I have to take the limit of, as b approaches infinity, of the integral from 1 to b of x squared e to the negative x cubed dx. And that's going to be, that's a classic u substitution. So that's going to be the limit as b approaches infinity of e to the negative x cubed. And the derivative is going to kick out a negative 3x squared. So we need a negative 1/3 because the x squared is there. And that's evaluated from 1 to b. Of course, that's equal to the limit as b approaches infinity of negative 1/3 times e to the b to the third minus the negative, which would be plus 1/3 times e to the first, which is just e. So as b approaches infinity, this goes to 0, and we get 1/3 to the e. And therefore, my original series converges because the integral converged. Okay, I think I'll end the video for now, and hopefully you're getting better and better at these.